go back to the problem statement. What are we trying to do? We are trying to get these two things to basically train themselves in a minimax game where they compete and they fight until the generator gets to a point where it's putting out data, piece of G, that is essentially indistinguishable by the discriminator, so that the distribution of fake data and of real data look essentially the same to the discriminator. That requires that we have some way of being able to measure how far apart are these two distributions, because ultimately the goal that we want is that these distributions should overlap and be identical or so similar that the discriminator cannot tell them apart. So in order to measure and compare the differences between distributions, we have a number of ways to do that. And one important way that we will be doing that is a measure that is called the KULLBACK-LEIBLER divergence. Let's go ahead and derive the KULLBACK-LEIBLER divergence, which is going to play a role in this analysis. First of all, we need a concept that's called information, an information theoretic definition. We all have an intuitive concept of what information is. There's one definition. Information, I equals to minus the log of P of X. Okay? So if I have an event, X, and I want to know what the information content of that event is, this is what the definition is from an information theoretic perspective, a la Shannon. Why does this make sense? Why is this valuable to us? Let's look at an example. Let's say somebody comes to tell you that if you know that it's been raining outside for days, right? And someone approaches you and tells you, I've got some great news for you, shocking news, very valuable information. Don't tell anyone, okay? It's wet outside. You're not going to be impressed. You would say, of course it's wet outside. I know it's wet outside. It's been raining for days and it's still raining. So you haven't given me any information. Tell me something that I don't know. Because what you just told me, I already knew. So you've given me zero information. How does this capture that? This captures that concept because if you know it's been raining outside, then the probability of it being wet outside is 1. It's 100% guaranteed in your mind. And therefore, this probability is 1. What's the log of 1? The log of 1 is 0. Therefore, what information did that person give you? 0. None. But how about this? If the person came to you and said, this is going to shock you. There's some natural phenomenon that happens once every 1,000 years. And despite the fact that it's been raining outside, if you go out there, you would be shocked that it's dry. The ground is dry. I'm making that up, okay? But different interesting things can happen. Now that would be very interesting. Why? Because in your model of the world, the probability of it being dry outside was just about 0. And this person comes out and tells you that it is actually dry despite all the rain. Let's put in our graph of minus log x. Okay, so this is minus log x, where x is your probability. The argument of the log. The argument of the log here is the probability of x. What's minus log of infinity? They've given you a massive amount of information. Why? Because the probability of what they have told you was nil. All right, so that's a good definition of information. Now, the KULLBACK-LEIBLER divergence is defined as the expectation of the information difference. So if there were 2 probabilities of an event, 2 distributions, they would carry different information. So there's a concept of an information difference, delta I, right? Which is, here I would say, I sub p. Let's put a little p here for the distribution. So I sub p minus I sub q. Say there are 2 distributions, p and q. and delta I is I sub p minus I sub q. I can expand that out, minus the logarithm p of x, that's I sub p minus I sub q, which is minus the logarithm of q of x, which is what? That's just the minus here, we have plus, so we have minus log p of x plus log q of x, right? And that's what? That is just minus the log of p of x over q of x. These are just the rules of logarithm I'm using. All right. So that's delta I, the information difference. And then therefore the expectation of the information difference with respect to q. With respect to q is, now we already saw what the expectation is and how it works. So I would now have here that the expectation, where we're sampling over q of x, of the information difference with respect to q of delta I, this is now the definition, we're coming up with this definition of the KULLBACK-LEIBLER divergence. It is what? It is simply the integral of, and I have this minus sign here, let's write the whole thing out. It's the integral of q sub x, q of x, delta I, dx, right? This term is called the KULLBACK-LEIBLER divergence, which I will write out here explicitly for us, KL for KULLBACK-LEIBLER, of this information difference. So it's q of x, p of x equals minus the integral of q of x, p of x, or rather log, I can't forget my logarithm, because we're multiplying by this, and this delta x is given by that, so we have here log p of x over q of x dx. And let's put that in a box, because it's vitally important for us. And that is called the KULLBACK-LEIBLER. That's the K in KL is KULLBACK-LEIBLER divergence. That's a term that very important and features multiply through AI systems, and so it's very important for us to have a good intuition of exactly where the KL divergence comes from, what it means, and the fact that what we use it for, which is for comparing the distance. It's a measure of the distance between distributions. How do they differ from each other?